Hello everyone, Dr. White back again with the third in our series of screencasts on section 4.3 on binomial distributions. In this screencast, we're going to examine expected value and standard deviation for binomials, and we're also going to look at considerations about the shape of a binomial distribution. First off, expected value and standard deviation. So remember, for any random variable, the expected value of the random variable is what you would get for the random variable on average in the long run if you tried it many, many times. And the standard deviation of a random variable, and that's called sigma for short, or SD for short, is about how much the actual value of the random variable will be, about how much the actual value of the random variable will differ from its expected value when you try the random variable. So it turns out that for binomial random variables, there are fairly simple formulas both for their expected value and for their standard deviation. If x is distributed as a binomial random variable with n trials and chance of success p on each trial, the expected value for x is just n times p, number of trials times chance of success. The standard deviation for x is a bit more complex. You have to multiply n times p times 1 minus p together, and then take the square root of all that. Let's try it on an example. Say you're planning to flip a fair coin 100 times and you're going to count up how many heads you get. Let's let x be how many heads you get in 100 tosses of a fair coin. So the expected value of x is n times p. For us, that's 100 times 0.5. That's 50. So that fits the intuition we've probably known since we were small children, that if you flip a coin some number of times, you can expect to get heads about half the time. But give or take how much? That's what most people don't know. But it's what the standard deviation can tell you. The standard deviation of this random variable x is going to be the square root of the 100 times the 0.5 times the 1 minus 0.5. In my mind, I'm going to think about this. 1 minus 0.5 here is also 0.5. So I've really got 100 times 0.5 times 0.5. So I think about 100 times 0.5 is a 50 because that's half of 100. But I'm multiplying by another 0.5. So I'm going to take half of that 50 and I get 25. Then I'm supposed to take the square root of all that. Square root of 25 is 5. So the standard deviation of this random variable is 5. The upshot is, when you flip a fair coin 100 times, you can expect to get around 50 heads, give or take 5 or so, for chance variation. 45 to 55 heads, totally standard outcome. 50 to 60 heads, that's what you're going to get practically any time. It would be really unusual and strange to get 70 or more heads or something like that. You can do this with R. You don't have to do these calculations on a calculator or in your head somehow or on a piece of paper. So here we are in the first code chunk, just finding the expected number of heads, 100 times 0.5. And for the standard deviation, you use the squirt square root function, parenthesis, 100 times 0.5 times the 1 minus 0.5 in parenthesis, and this closing parenthesis is matching that opening parenthesis for the function. And you get out your 5. So if you're working in the DA and you need to calculate an expected value or a standard deviation, it's fine. Either use a code chunk that's there or make a code chunk and do these calculations, and in the knitted output, the answer will show up. The shapes of binomial distributions, our second topic for this screencast. I want you to explore this little app that's given by a function in the TigerStats package, binom norm. You call the function just with parentheses. You don't have to put any inputs in it. Copy, head over to our studio. And I tell you what, before I run this function, I'm going to make my graphing window a little bit bigger for you here. And I paste in my function and run. Okay. So what we've got when things open up is a little stick graph to give you the distribution of a binomial random variable with 5 trials, 20% chance of success on each trial. So the number of successes is here on the x-axis. The possible number of successes is 0, 1, 2, 3, 4, and 5 is also possible. Now, the height of each stick is the chance of getting that exact number of successes. So the chance of 0 successes is a little bit more than 30%. Chance of 1 success is about 40%, and so on. The chance of 5 successes was so small that the graph just decided not to even try to show that stick. All right, so there's a little graph of the distribution of this binomial random variable. Now go to the cog, click on it, and you get some manipulators. You can choose the chance of success P. It can be anything from 0.01 to 0.99. You can also choose the number of trials. It can be anything from 1 up to 1,000. You can also show a normal curve that has the same mean and the same standard deviation as the binomial random variable whose distribution you're looking at right now. I'm going to click that. The normal curve is symmetric. The binomial distribution is rather skewed. There's a skewness out to the right, a little tail going off to the right for the binomial. So they're pretty different types of distributions right now. But what I'm going to do is I'm going to move the number of trials up. Okay, I've gone to 1 trial there, but I'm going to, now that I've got my focus on that, that little marker, I'm just going to use my right arrow. 2 trials, 3 trials, 4 trials, 5 trials like we started, 6 trials, 7 trials, 8 trials, 9 trials, 10 trials. So I'm looking now at a binomial random variable with 10 trials, 0.2 chance of success on each trial. 10 times 0.2 is 2. I'm expecting 2 successes, and sure enough, the rectangle over 2 is pretty big, and so are the rectangles near it. Next up, 11, 12, 13, and I could go that way. I'll go on up to about 20 trials with my little right arrow key. And what you'll notice is that the sticks that make up the distribution for the binomial random variable are starting to align themselves to be closer and closer to the normal curve that has the same distribution, that has the same expected value and the same standard deviation as that binomial. The two are getting closer and closer. I can just move this slider. I moved it up to about 165 trials. And now I can hardly tell any difference between the heights of the sticks and the heights of the normal curve. I could go up to 1,000 trials, and there's basically no difference at all. The bigger the number of trials got, the more the distribution of the binomial random variable resembles a normal random variable with that same mean and same standard deviation. Let's move it back to a small number of trials. How about, say, just 10 trials? And let's move the chance of success way down to 0.01. That's a super skewed to the right binomial distribution. Almost really big chance. Looks like over a 90% chance to have no successes in your 100 trials, in your 10 trials, and a little chance of having one success, practically no chance of 2 or 3 successes. Very different from a normal curve. But now let's move the number of trials up. How about to about 85? How about to 198? How about to 341? How about to 521? How about to 1,000? Wow. The higher the number of trials, the more the distribution of the binomial random variable is resembling a normal curve. The correspondence isn't perfect looking now, but I think if I could have taken my number of trials up to 2,000, 3,000 or more, that the binomial distribution would continue to look more and more normal. Even though the chance of success is way small, if you let the n get big enough, you will see the binomial distribution approaching the normal. Let's go down to a small number of trials again and move the chance of success way high. Now for this binomial random variable, the distribution is left skewed. You can see the tail of sticks going off to the left. But if you move the number of trials up, you again see that the binomial distribution has approximately a normal distribution. None of this is any accident. The fact is that no matter what p is, as n gets larger, the distribution gets more bell-shaped, more like the normal curve. A lot of people think that it's going to look pretty bell-shaped as long as n times p is at least 10 and n times 1 minus p is at least 10. That's what most people do when they kind of are looking at these curves. The times it looks normal, the times the binomial looks normal to them are when both of these things happen. N times p at least 10, n times 1 minus p at least 10. Now n times p is familiar. That's the formula for the expected number of successes. N times 1 minus p is just the formula for the expected number of failures. So we could make a little 68-95 rule for binomial random variables. Let x be any binomial random variable. If the expected number of successes and failures for the random variable are both at least 10, then there's going to be about a 68% chance that x will be within 1 standard deviation of its expected value, and about a 95% chance that it'll be within 2 standard deviations of its expected value, 99.7% chance of being within 3 standard deviations of its expected value. For example, say you flip a fair coin 100 times, let x be the number of heads you get. So we've calculated that the expected value is 50 and the standard deviation is 5. And we have seen pictures of the distribution of this binomial random variable. It looked pretty bell-shaped. And hey, the expected number of successes is way more than 10. The expected number of failures is also 50, way more than 10. And so that 68-95 rule applies pretty well. So we can say, even before we use something like p binom GC, we can say there's about a 68% chance that you'll get within a standard deviation of the 50, within 5 of the 50, between 45 and 55 heads. About a 95% chance of getting within 2 standard deviations of the 50. 50 minus 2 5s is a 40. 50 plus 2 5s is a 60. About a 95% chance you'll get between 40 and 60 heads. So you can tell a lot about probabilities for a binomial random variable just using its expected value and standard deviation, as long as the distribution of the binomial is roughly bell-shaped. That'll happen if the expected number of successes and failures is both least 10. Here's just a little check and a reminder, because we've done this calculation before. P binom GC can tell you the exact chance of 45 to 55 heads, including the 45 and 55, and you may remember that it turned out to be about 73%. 73% as opposed to 68%. That shows you some of the limitations of the 68-95 rule for binomials. It's kind of having to deal with those boundary rectangles possibly being big. I want to remind you before I go that there is a useful tutorial on P binom GC at this URL here on the website for TigerStats. So if we were to follow it, then we could consult the table of contents to learn how to find all kinds of different binomial probabilities, like the probability of being less than or equal to a number, bigger than or equal to a number, less than a number, bigger than a number, between two numbers, and exactly a number. Again, it's all part of the TigerStats webpage. You can also find it under vignettes, P binom GC. That's all for now. See you later.